Alright, video number 5 on FPGAs, and this would be the last video on FPGA architectures. So I took the slides from Peter Chung of Imperial College, and I have chosen a slides from his. So I've posted the whole set on Moodle, but I'm only going to go through a couple of these slides. So this is an interesting slide. This basically shows that back in the old days, your FPGA was being only used for glue logic, and glue logic is basically stuff that are not on the critical path, and you needed to basically connect different components together. And that's when the FPGAs were very small, 16K logic elements, and 50 megahertz was the range of numbers that they could provide. But as FPGAs became more powerful and bigger, 40K lookup tables and 100 megahertz. This was back, oops, sorry, and this was back before even 2000, I think. Then FPGAs started being used in control logic. Then you had data path, and right now you have heart of the system. Basically, when FPGAs can deliver 300 megahertz and have 330K logic elements, then they can be used as end products. So when you had FPGAs in glue logic, basically primarily FPGAs were being used for prototyping, and then we had those multi FPGA boards that had 4 or 8 or more FPGAs on them, and people would just prototype the system instead of doing the software simulation. They would do run it in hardware. But right now what you have is not just prototyping. Cisco has actual FPGAs in there, some of their routing stuff. So this could be for as the end product. FPGA is able to deliver the performance. Could you all right. And then, so one of the questions that you might be asking is, if when I showed you the older FPGAs, we had 4 lookup tables, 4 LUTs, and nowadays people talk about 6 LUTs and 7 LUTs and 8 LUTs. And the question is, what type of logic are you going to be using in a particular benchmark? So this is a slide from Altera, and basically shows you 2 different synthesis results. So in the black ones, you synthesize for speed, and in a blue one, your primary target is minimize area, right? So if you think about it, if you want speed, basically what you want to do is you want to pack as much logic into a bigger LUT. So you would like to use more 7 LUTs, because if you use 7 LUTs, essentially what that means is that if you have NAND gates feeding, XOR gates feeding OR gates, right? All of these feedings, basically you're covering a bigger subtree, and all of the connections between those logic elements would be hidden. Right. So basically, I mean, if you think about if you think about gates, and we had our technology mapping slides as well, right? I mean, if I have a bunch of gates, and these gates are implementing something. Now, if I want to cover this whole tree, then I need 6 inputs, right? So I can put the whole thing into one 6 lookup table and hide all of these connections in between. But if I want to use 4 LUTs, then I basically have to put this into one lookup table, then these into another lookup table to utilize area better. So when you use a lot of 7 LUTs, basically that means that sometimes you're just using 6 of the inputs in the 7 LUT, or some of the logic elements inside your CLB are being unused, so that would not be too efficient in terms of area. But because you're hiding a lot of these connections inside the lookup table, then things do get better. But at the same time, I mean, if you take one design, not everything is going to be mapped to 7 LUTs, right? I mean, some parts of the circuit graph make sense to be only done, using 4 LUTs or 5 LUTs and so on. So you would see that you do need a mixture of these, and that's one of the reasons that these FPGA devices allow you to use a 6 LUT basis and then combine them into 7 lots and 8 lots if needed. As you combine them into 7 lots and 8 lots, you're wasting some of the routing resources. If you remember, you had the 7 lot, for example. You would use two 6 lots in parallel, but you're sharing the exact same inputs to both of them. So that basically means that the extra flexibility that the FPGA provided is being wasted now. Now, if you look at the Altera's version of the CLB, so the CLB in Xilinx, configurable logic block, has the same functionality as ALM. And ALM is basically arithmetic and logic module, and this provides you the LUT, 8 input fracturable LUT. So you see the same story, right? I mean, you have an 8 lot that could be broken into 6 slots or 7 lots and so on. And then you have fast adders here. You had a similar methodology, you had a similar structure in Xilinx. And then you have registers that you may or may not bypass, right? So you could use it for different reasons. And then this is how you can break it up, the ALM, into 4 lookup tables, 2 4 lots, 1 6 lot, 1 7 lot, and any of these sharings of the inputs, and so these are the different ways that you can implement lookup tables, and this is how you can use it for adders. So basically these would be, carry in, carry out, the carry chain, and then you have your ABCDs that you would use to do addition. Now, the question of why we no longer use 4 input lookup tables and we use 6 input lookup tables. I partly alluded to this when I talked about hiding some of the interconnects between the logic that you map in here, right? And if you think about the trend in the technology and the fabrication, what happened was that your transistors got smaller, so that meant that your LUTs became a relatively smaller part of the overall logic, and interconnect started to dominate. So if you have small amount of logic being computed inside a for lookup table, and you need to go through a large interconnect network which has high capacitance and high delay to get to another for lookup table, then it becomes less and less appealing. In today's world, with today's technologies, 4 lot is not going to be useful. You need at least 6 slots, and that's how FPGA companies adapted, and they started using larger LUTs. And if you think about, increasing it to 6 slots, basically the Vertex 5 family started using 6 slots. This is the percentage of this is the number of LUTs that you need to implement things like this. So if you need a 16 input mux, you would need 8 of the LUT 4, but only 4 of the LUT 6. And that's a reduction of 50% in terms of the number of CLBs essentially that you will end up using. And then they had microblaze and DES decryptor and so on and so forth. So basically when they looked at these different benchmarks, they saw that yes, I'm going to be able to do more reduction in terms of the LUTs used. So that again determines that you want to use a 6 lot or 7 lot or 8 lot, and this study is going to be repeated every couple of generations, because things that might have made sense with the previous technology might no longer make sense with the new technology. This is Altera's mix of memory and DSP and so on, and the text here might not be readable, but essentially what this is you have basically dual port memory, small memory blocks that you can use, and then this would be the logic elements that you have, the cluster of logic elements that you have. These would be the DSP blocks doing multiplication and so on, and you can see that there is a big mega RAM block, 512K RAM, and again you can see that the heterogeneity of the structure, and one thing that is similar to what Xilinx had. Remember, Xilinx arranged all the block RAMs into one column. Same thing is happening here. Now the routing structures are different. So for example, the labs, as far as I remember, they have 10 of these ALMs as opposed to 8 that you find in Xilinx FPGAs. And also the routing architecture looks more like a hierarchical design compared to the flat that Xilinx has, but otherwise pretty similar in terms of the features that they provide. Now, this is interesting, especially for the group who are doing the analytic placement for FPGAs. Um, one of the things that they think about when they design the routing structure is how much delay you would have to incur to connect a logic block to another logic block, let's say 10 horizontal units to the right and 3 vertical units to the going up, how much delay you have to go through, how many hops do you have to go through, how many of these switch boxes you have to go through. So if you start your signal here, if this is the source of the signal, and your destination signal is here, you have to go through 3 hops, and the number of blue logic elements that you can reach is going to be 4,000, right? So this is one architecture that they had in Stratix 3, and this is Xilinx's Vertex 4. So in Vertex 4, they didn't have any diagonal routing. So in order to reach a logic, let's say here, they had to go through 3 hops. And you can see that this is far from a Manhattan distance delay, right? So this looks nothing like Manhattan distance, and that's one of the reasons that doing analytic placement for FPGAs becomes challenging. But the good news is with Vertex 5 and their providing of the diagonal connections, this looks a whole lot more like Manhattan routing. So it's easier to adapt analytic placement to more modern FPGA architectures compared to Vertex 4. And that might be one of the reasons that analytic placement didn't happen with FPGAs as readily as it happened with ASIC, because when analytic placement was very hot with ASIC, that's when Vertex 4 was around. But this I'm sure if this was the case, the Vertex 5 had been the prevalent architecture back then, I'm sure analytic placements would have been much more prevalent with FPGAs. And of course, I mean, the same thing happens with the actual delays that you have to go through. So basically what they say is that I have a certain dimension in which I can basically reach the signal in 565 picoseconds, and beyond that I have to go through the first ring. They just put a cutoff limit, cutoff number on how slow it would be, and basically they would say, this is how many picoseconds I need to get to the signals. This is what you really want, right? Not necessarily the number of hops that you want. This is the actual number that you're interested in minimizing. All right, now power is another big issue, because with FPGAs you want them low power. And essentially a number of things would happen as you migrate from an older technology to newer technology, right? So the transistors go down, and the cause of that is you're migrating from 90 nanometers to 65 nanometers, for example, right? And then the effect would be that your leakage would go up because you have thinner oxide, shorter channel transistors, so your leakage naturally goes up, and now you have to deal with these issues, right? You want your FPGAs to be low leakage but fast at the same time. Obviously speed goes up, but at the same time dynamic power goes up because it's C VDD squared F, and your frequency is going up, right? Your density goes up, which means that you have more transistors that are switching, so your dynamic power goes up. So in the next couple of slides, Peter Chung talks about what techniques Altera and Xilinx use to minimize the power, especially leakage power. So if you think about the speed at which your lookup tables and your FPGA switch boxes and routing structure have to work at, it's basically, this is the slack. If you do the histogram of the slack of the design, there are only, a few paths that basically, less than 1,000 paths that need to be very fast, but the rest of the design has low performance requirements. So the critical paths are here. By the way, this would not be the histogram that you would see in an ASIC, right? In an ASIC, you would try to you start with a slack like this, right? And then you would focus on making these guys faster, right? So you would change the profile of timing to be something like this, right? And then again, you would say, let's push the limit, let's make these guys faster and faster. And then your profile then would look something like this. And this is called a timing wall. If you want to improve things, now you have a whole lot more paths that you need to optimize compared to the case here in which you only had a few gates here that you needed to optimize. But these are, some of the limitations of the FPGAs that you can't, get the most performance out of it. And that's one of the reasons that FPGAs are lagging behind ASIC in terms of performance. All right. So basically, what Altera said was, if I can run things on the high-speed logic, only these red path gates are taking advantage of the fact that the logic could be very fast. The rest of them are not on the critical path, so you're just pumping it too much power into it to make it very fast, which you don't need to. So if I have a choice of making some of these logic elements go slow and have low power, for example, by changing the VDD or changing the back body biasing or whatever techniques that you can use, basically you can save in terms of power and yet not lose on the speed, because the ones on the critical path are still running fast on the high speed logic, which consumes more power. So that would be a good solution. And if you look at this picture, a lot of these logic blocks are not even programmed to do anything. So they can go in a very, very ultra low power state and minimize the leakage that they're going to cause. So that's the Altero solution. And basically what they say is they provide two power rails essentially. One of them is going to be 1.1 volt, one of them is going to be 0.9 volts, and you could basically run the core at these, sorry, they don't, I think I'm wrong. They don't provide two separate power lines. This is the same power network that is running on these two different different voltages. I'll check back, and if I'm making a mistake, I'll fix it later. And if you look at this, basically using these power optimization techniques in a statics 2, as the number of logic elements goes up, so does your static power, right? But then by using these low power techniques of, using the fast versus the slow logic elements, you can bring down the profile like this. And if you run it at 1.1 typical, as opposed to the low power design, this is the one that distinguishes between the fast and the slow ones. This is the power profile, and if you run it at the low power, low speed mode of 0.9 volts, then this would be the power profile. So significant reductions in power. Xilinx did focus on the gate leakage. So basically what this graph shows you is that this is the temperature, right? And this is around room temperature around here, and you have your leakage, source to drain leakage, and you have your gate leakage going on here, right? And if you look at lower temperatures, your gate leakage dominates, right? And you don't want that. A lot of times your FPGA is not doing heavy lifting computing, so its temperature might not be high. And C grade means commercial grade, I grade means industrial grade. So these are the temperatures that you would expect industrial designs to be at. And essentially, Xilinx said, let's focus on the gate leakage and try to minimize it so that I can get rid of a lot of this curve and improve things. And they did that by basically looking at the functionality of different components in your FPGA. So you have your configuration memory that needs to be low leakage, right? You don't, and the configuration doesn't change its values. Once you program your FPGA to do, FIR filtering, you don't want to go back and change that to IIR filtering every cycle, right? I mean, you would change configurations very infrequently. So those need to be not necessarily very fast, but you want them low leakage, right? But the logic that actually is going to do the computation, you want that to be fast. So you would use thin oxide, which does a lot of leakage. And for I/O blocks, you want your maximum voltage tolerance, lowest leakage. So you would use a thick oxide there. So by using the different oxide thicknesses, they can provide a good mixture of performance and reduce leakage. Now in the newer technologies, Altera, for example, has teamed up with Intel to use their fab and the 3D transistors that they have. So we're going to see more and more power being important. And of course, I guess one of the markets that FPGAs might get into would be and in fact, some companies have gotten into, but not Xilinx and Altera, would be the mobile, the handheld devices. And if you want to put an FPGA into a handheld device, it better be low power. You don't want your cell phone battery drained because you use the FPGAs. These are some of the references that Peter Chung used to put up the slides. I included them here. And again, as you saw with the Xilinx slides, I didn't go through everything, but skipped over a bunch of the slides. I highly recommend that you go over the whole thing and take a look. All right, this would be it in terms of the FPGA architectures. I'll record another video on FPGA CAD later. Thank you.